So, good morning, good afternoon, good evening. This is Keeping an Eye on the Universe. This is the fourth in the series of the universe half an hour at a time. I started by talking about the beginning of everything and how in 3 minutes all the hydrogen in the universe was made. And then in the second talk I described how that hydrogen made all the stars and all the galaxies. And last week I talked about black holes and dark matter. This week we'll be looking at how telescopes inform us about what the universe is up to. Now we know Galileo started this all. He didn't invent the telescope, but he was one of the first to point the telescope at the night sky, and he was certainly the first to record his observations in detail, telling us what the universe was doing. In the 400 years since then, telescopes have changed quite considerably, not least changing lenses to mirrors, and in the last century or so, telescopes have got ever larger. From the 2.5 metre or 100-inch Hooker telescope that Hubble used to determine the expansion of the universe, through to the 5 metre or 200-inch telescope that for something of order half a century was the largest telescope in the world. In the last few decades we've got used to the idea of space telescopes, like the Hubble Space Telescope that's now been in orbit for over 30 years. Hopefully soon to be joined by the James Webb Space Telescope, not as some people might think a successor per se, but because the James Webb will be working mainly in the infrared part of the spectrum rather than the visible part of the spectrum, the James Webb is more a complement to the Hubble Space Telescope rather than a successor. And here on the ground, telescopes continue to get larger and larger, and in a little while we'll be seeing monsters like this one, the 40-metre diameter European extremely large telescope. We can see how mirrors have got larger and larger in this graphic, which shows telescopes, major telescopes over the last 100 years. In the very top left, we have the Hooker 100-inch and the Hale 200-inch. And over on the right there, we see the European extremely large telescope, the largest telescope currently under construction. The largest telescope currently in operation is this one at the top, Gran Telescopio Canarias. It's about 10 metres in diameter. We can't strictly talk about diameter because, as you can see, it's actually made up of a large number of smaller segments, each of which is hexagonal. But that gives you a rough idea of the size of the main mirror. The drive to make telescopes larger and larger is driven by the fact that larger mirrors will be able to catch more light, so we'll be able to see fainter objects, and also a larger mirror should be capable of higher resolution, so seeing more detail. Compared to most of the telescopes we can see in this picture, the space telescopes, which are down in the bottom left corner, you can see 4 of them there. There's the Hubble 2.5 or so metre diameter mirror, relatively small. The restriction simply that it's difficult to take a telescope and launch it from the surface of the Earth into space. So there's a limit to how large you can make these telescopes. The Webb Space Telescope will have a somewhat larger mirror, and that, unlike the Hubble, it won't be in Earth orbit, it'll be sent to the so-called Lagrange L2 point, which is where Gaia is currently mapping out stars in the Milky Way. So let's have a look at one particular telescope and some of its images. There can be very few people who don't recognise the rather iconic outline of the Hubble Space Telescope. I would argue even people who are not particularly interested in science or astronomy may well still recognise this telescope and some of the images it's produced over the last 30 years. One of the most interesting has been the Hubble Deep Field. In this particular case, the telescope was pointed to a patch of sky where it was assumed that there was nothing particularly interesting going on, and the longest possible exposure was taken, some 1 million seconds, or about 10 days equivalent exposure. And what we've captured here, apart from perhaps 3 or so stars in our Milky Way galaxy, every other object you can see here is a galaxy in its own right. Some of those galaxies are quite close to us and quite bright. Some of the fainter galaxies are probably a great distance away from us. Some of them are many billions of light years away. And so the light has taken billions of years to reach us. And so in a very real sense, this snapshot is looking back in time. Some of those galaxies might be 10 billion light years away, or at least the light has taken 10 billion years to reach us. And so we're looking back to the earliest stages of galaxy evolution in the universe. And we can compare images and images of galaxies at various distances. We can compare those with simulations to see if we've got our understanding of the universe about right. We have to bear in mind that this is a relatively small field of view. If we think of the field of view relative to the full moon in our sky, which subtends about half a degree, then the field of view of the Hubble Space Telescope is quite tiny by comparison. And hence, if in the Hubble Deep Field we can image many thousands of galaxies, then by knowing the field of view we can work out, roughly speaking, how many galaxies there are in the entire observable universe. And it turns out to be many hundreds of billions, perhaps as many as 1 trillion galaxies. Just to prove it wasn't a fluke, they also took an image of a different patch of sky and again a very long exposure. And again, the details might be different galaxies, but the big picture is essentially the same, telling us that no matter where we look in the sky, we see approximately the same thing. In other words, we're not in any particular special place in the universe. Wherever we look, on the largest scales, we see the same sorts of structures. If Hubble looks at just one of these galaxies in more detail, one of the closer galaxies, then because of the resolution of Hubble being above the Earth's atmosphere, none of the turbulence of the Earth's atmosphere can degrade the images. So we get wonderful detail, and we can look in detail at the structures of, in this case, the spiral arms of the galaxy. And if the galaxy is close enough, we can see individual stars within the galaxy itself. Many galaxies are not isolated like this one, but are often found interacting with neighbouring galaxies. For instance, the galaxy at the top here, its spiral arms appear to be distorted by the presence of the galaxy towards the lower part of the image. Tidal effects are disrupting what would otherwise be rather symmetrical spiral arms in the galaxy. And some galaxies are seen in the process of collision. Here, 2 galaxies are colliding with each other, and although at first sight we might think that galaxy collisions sounds rather dramatic and sounds like the end of life of a galaxy, quite the opposite. Galaxy collisions are a natural part of the evolution of galaxies. And in this particular case, we can see from the pink regions showing up here, these are stellar clouds where star formation is rife. So the act of galaxies colliding with each other can actually induce new star formation. So far from being the end of life of a galaxy, we can think of galaxy collisions and mergers as being a sort of rebirth, if you like. Looking within the Milky Way itself, the Hubble has been able to image in great detail planetary nebula like this. Nothing to do with planets. This is a shell of gas that was, some time ago, the outer part, the outer layers of a star. When a star like our Sun comes to the end of its life and the nuclear fuel starts to run out, the star can expand into a red giant and the outer layers can be lost into interstellar space. So what we're looking at here is a large hydrogen cloud, mainly hydrogen, but also enriched with all of the elements that were made during the star's life. Hydrogen might have been fused into helium and helium into heavier elements, and those have now been reseeded and recycled back into the space between the stars. This is what we think is the ultimate fate of our Sun, and so in a sense we're looking at what the Sun will be in a few billion years' time. Stars that are more massive than our Sun might end their lives not by shedding the outer layers in a planetary nebula, but in a more catastrophic supernova explosion, in which case, again, all of the material that was inside the star, all of the heavier elements that were made by the star throughout its life, get recycled back into the interstellar medium. And this image, although it shows a great deal of detail in this particular supernova remnant, the Crab Nebula, I think one other supernova remnant actually shows more interesting detail. If we look at the Veil Nebula, the inset shows the entirety of this supernova remnant, a large spherical shell of gas that was ejected when the star went supernova. This, in the inset, is quite a large field of view. It's many degrees across, much bigger than the full moon, so far too big for Hubble to image all of that nebula. But if we look just inside the red rectangle there, that's what we're looking at in the main image. And we can see a number of different colours within this particular part of the supernova remnant. And each colour colours a particular element. So for instance, in this case, hydrogen has been coloured red, and sulfur has been coloured green, and oxygen has been coloured blue. Each of these are taken with different filters to only let through the light from those particular elements, and then each image is coloured to produce this final colour image. So we can see not only the fantastic structure, which tells us about how this material that was ejected in the supernova perhaps thousands of years ago, not only how that material is expanding, but because that material is expanding into the interstellar medium, the very tenuous gas that exists between the stars, we are actually seeing the shock waves as this material is expanding outwards and hitting the interstellar medium. So images such as this give us an enormous amount of information, not only about the star that produced the supernova, but also about what's going on in the space between the stars. One of the most interesting aspects of Hubble's imaging over past years, I think, has been the proof of gravitational lensing. This was forecast by Einstein when he produced his theory of general relativity. He said that large masses will distort or curve or bend space. And as a result, any light passing through the region will also undergo bending because it's following the curve of space. And Hubble has found many interesting examples of precisely that. In this case, all of the orangey blobs here are the clusters that are galaxy in a large cluster, and we're looking at more distant galaxies where the light has been passing through this galaxy cluster. And we can see in this little white box here, there's a particular galaxy. And because the light from this galaxy is taking different paths as it's bending through this galaxy cluster, the galaxy itself is imaged more than once. The galaxy is in that white box, but it's also imaged here, top left of the white box. And also this galaxy further away up here is also the same galaxy, but the light has simply taken different routes as it came to us from the distance to, in this case, the Hubble Space Telescope. Not only that, but when we look in detail at this particular image of the galaxy, we notice that there happens to be one galaxy in the foreground just on our line of sight to that distant galaxy, and we notice these four bright spots. These are supernova, or at least they are not four different supernova. The likelihood of that happening is very remote. In most galaxies, a supernova might occur perhaps once every century. So the chances of one galaxy exhibiting four supernovae at the same time is extremely unlikely. What we're looking at here is another gravitational lensing effect, and we are actually observing the same supernova 4 times. So lots of images like this have enabled us to verify that Einstein's theory of general relativity is essentially correct. Not only that, but images like this have given us another key element of how the universe works. And if we were to calculate how much mass must there be in this galaxy cluster in order to bend the light to produce these multiple images of the galaxy, or the multiple images of the supernova. The amount of mass that must be present is far more than we can account for simply by looking at all the galaxies themselves. Far more by a factor of 5 maybe, or sometimes a factor of 10 greater. This is the missing mass, or the so-called dark matter, that we deduce must exist even though we cannot see it. Perhaps more iconic than the images that we've seen up till now have been the images that Hubble have produced of nebulae within our own galaxy, such as this one, which has become known as Mystic Mountain, which is part of the much larger Eta Carina Nebula. And again, what's happening here is that different elements are being imaged, and different elements are then assigned a particular colour. In this particular case, sulfur has been assigned the red colour, hydrogen has been assigned green, and oxygen has been assigned blue. So not only does it, in beautiful technicolor, reveal the structure, it also tells us about the chemistry of what's going on in structures like this. And perhaps even more famous than that one is the Pillars of Creation, a similar structure that's seen in the Eagle Nebula, which is visible from more northerly latitudes. And what's going on here is that we have very dense regions of gas and dust that have been sculpted by the very strong winds from young hot stars that are embedded within these structures. But of course you can see the problem is we can't really tell what's going on because these structures are so dense, light is scattered so strongly, we can't really see what's going on inside. And hence we, some time ago, thought about a new space telescope, not to supersede the Hubble, but to complement the Hubble by working in a different part of the spectrum. That's how the James Webb Space Telescope came to be. Hopefully we will see that launched in not more than a few months' time. The James Webb will be working in the infrared part of the spectrum, and because of that it'll be sensitive to heat, and so we don't want to put it in Earth orbit. The Earth is a very hot object and it will be radiating a lot of heat, and that heat will mask any of the faint objects that the James Webb is trying to observe. So the James Webb is going to be taken out to the so-called Lagrangian L2 point, which is well away from the Earth, beyond the Moon, and when those sun shields that you can see below the telescope there, when they are deployed and correctly angled, they will block the heat from the sun and the Earth and the Moon and allow the telescope to stay very cold and then operate successfully in the infrared. The James Webb mirror is substantially larger than the Hubble mirror being only 2.4 meters in diameter. You can see the James Webb telescope is of order 6 meters in diameter, very much larger, meaning it will be able to collect much more light, and also it'll have a much higher resolution. And what will the James Webb Space Telescope do? Well, I've already given an indication of one of the things it will be able to do. In visible light, we find it difficult to see into these nebula, into these star-forming regions, these stellar nurseries, if you like. And with infrared light, which is less affected by the scattering effects of the gas and the dust, we'll be able to see inside these structures and see the stars. So these are the same field of view, but you can see so many more stars on the right compared to the left because of the ability for infrared to see through the gas and the dust. So not only will we get a better idea of star formation in these regions, early stars will be starting to form planets as well. And when planets are forming, again, that's a very dusty environment, and again, visible light is not the best way of seeing exoplanets in their early stages of formation. So again, the James Webb will be applied to looking at the origins of exoplanets. And another area where James Webb is expected to excel, if we think about the Hubble Deep Field, remember we said that some of these brighter galaxies are quite close and some of the fainter galaxies are quite distant, many billions of light years away. Well, because of the expansion of the universe, some of those distant galaxies are receding from us at very high velocities. Some of them are receding faster than the speed of light itself. And because of the phenomenon of redshift, because these objects are receding away from us, then the wavelengths of light that they emit will be stretched. And so any young hot stars in those early galaxies that might be emitting in the ultraviolet or the visible part of the spectrum, their light is going to be stretched out to longer wavelengths and redshifted into the infrared part of the spectrum. So we expect some of those very distant galaxies to be brighter in the infrared than they are in the visible. So if the James Webb were to take a similar picture to this one, we would expect those distant galaxies to be much brighter. And hence the James Webb will be able to see more of those galaxies, and hopefully we'll be able to see more distant galaxies. And remember, the greater the distance, the further back in time we are looking. So it's hoped that the James Webb will be able to see even earlier epochs of the universe, back at the point where the first galaxies and the first stars were starting to form. We have to bear in mind that space telescopes, like the Hubble, like the James Webb, they have a limited field of view. If we want to see everything that's out there, we can't expect space telescopes to do all the work. If we wanted the Hubble to map out the whole sky, it would take centuries for it to do that. What we need are survey telescopes that are capable of surveying everything in the sky on a much more rapid timescale. And that's why this telescope is being constructed currently in Chile. The so-called Large Synoptic Survey Telescope, since been renamed the Simonyi Telescope. But the acronym for the Large Synoptic Survey Telescope, the LSST, has been so widely used in the past years, it was decided to keep the acronym, but to repurpose, or upcycle if you like, the acronym, which now stands for the Legacy Survey of Space and Time. In other words, this telescope is not only going to map out all of the sky that it can see from its site, it's going to do that over and over and over again so that it can see things changing, stars changing in brightness or objects moving through the solar system, for instance. It's going to achieve a survey of the entire sky that it can see in only 3 nights. Whereas the Hubble might take centuries to do the same thing, this telescope can do it in essentially 3 nights. How does it do that? It does it because it has a huge field of view, thousands of times bigger in terms of its area covered compared to the Hubble. How does a telescope achieve that sort of field of view? Well, one thought that has to be taken is to how the optics are designed and how big the detector is. If we see the result of the Hubble Space Telescope field of view there, and we ask how big a field of view can we obtain if we have the right mirror and the right detector, the field of view we might hope for can't fit on this slide. Only a little bit of the arc of the edge of the field of view is visible, but you can see that it is thousands of times larger than the Hubble field of view. So that will be achieved by thinking about how to design the mirror. It's going to be an 8-meter diameter mirror. That's the mirror before it was figured to the right shape and then coated with aluminium. But also we have to think about the detector. No, that's not it. Just for scale, that's a reminder that the camera that you have in your mobile phone is tiny and has a sensor, has a detector that might only be 1 millimeter or 2 in size. By comparison, the detector in the Hubble Space Telescope in camera number 3 is that sort of size, 40 by 40 millimeter, 4 by 4 centimeters, and it contains about 16 million pixels. Now, that might not sound too impressive. For those of you who've got a digital SLR camera, you might have a camera which has perhaps more megapixels than that. It might conceivably be a fraction of this size, perhaps a few centimeters on a side. But we're just using that as a reference to remind ourselves that if that is what is in the Hubble Space Telescope, let's think about the size of the detector we would need in the LSST if we want to survey much larger chunks of sky. So let's start with that 16 megapixel chip and use that as a basis, and let's say what would happen if we added another 8 of those together. We would end up with a little collection of CCDs. Now let's take that particular collection and think about adding another 8 of those, and then another 12 of those, and then a few more chips to make sure everything is in focus and the telescope is pointing in the right direction. What we end up with is a detector which is truly massive. So the Hubble Space Telescope, remember, was that size. The detector we're talking about for the LSST is so large I don't think I can even get it into this camera field of view. There it is, a one-to-one mock-up of the size of the detector for the LSST. Absolutely huge, the size of a coffee table. And I can't show you the sort of images, even simulated images, for what this is expected to do when it comes online in a few years' time. Because of course, if this particular detector is going to generate not a few megapixels, but 3 gigapixels, 3,000 megapixels if you wish, I can't possibly show you even a simulated image because my monitor can't take that resolution and Zoom certainly can't screen share it to you. All we can do is to say, let's imagine taking a tiny fraction of the total image that this would produce. That little black square just left of center, let's imagine what that would show us if we took an image. In a single 15-second exposure, this is what we might see. And remember, the full image that we get after 15 seconds would be some 3,000 times what you're looking at the moment. It will catch, in its 15-second exposure, millions of stars. It will catch millions of galaxies. It will catch thousands of solar system objects like asteroids and Kuiper belt objects and trans-Neptunian objects. It will probably also catch a few supernovae. If we bear in mind that if we add up all of the supernovae that have ever been detected by all telescopes in the history of telescopes, add up everything in the last 400 years, that total comes to about 1,000 supernovae. It is expected that when the LSST is in operation, it will probably detect 2,000 supernovae every night. In one night, it will catch more supernovae than have ever been seen before by all telescopes put together. And this telescope will be operating every night, every clear night, for nominally 10 years. During that time, it will be able to catalogue tens of billions of stars. And by catalogue, I mean record their position, record their brightness, record their colour. And similarly, tens of billions of galaxies will be recorded. And because the entire sky will be mapped every few nights, it'll keep doing that, and so we'll have a time sequence of how stars are changing, how galaxies are changing, how objects are moving. In addition to producing a vast catalogue of objects that are out there and surveying, scanning the entire sky, which by the way will generate enough data to fill something like 20 terabyte disks every night that it's in operation. In addition to doing that, it's hoped that on the largest of scales, the LSST will be able to answer some of the questions we have about dark matter. This is only an artist's impression because we don't know where all the dark matter is. Maybe it's uniformly spread throughout all of the galaxies. Maybe it's clumped and certain satellite galaxies have a lot of dark matter around them. The bottom line is we don't really know. But by imaging lots of galaxies at different distances, remember galaxies will distort space and thus will distort the images of galaxies at greater distances, we should be able to figure out where the dark matter is. And by looking at different distances, we're looking at different epochs back in time, so we can get an idea of how the distribution of dark matter has changed. And we believe that dark matter distributions will change because of this elusive thing that we call dark energy. And we don't really understand what that is, but it seems to be an element of the universe which is causing the expansion of the universe to accelerate, and we think it will also influence how dark matter is distributed throughout the universe. So one of the things that the LSST is going to do, if we can't see where the dark matter is, we think, because of simulations that have been carried out, we think the dark matter on the largest of scales is arranged into a sort of a cosmic web, a web of voids and filaments according to this red structure that we can see here. But of course we can't image that directly. What we can see are individual galaxies. And because the dark matter will distort space and will distort the view of more distant galaxies, the intention is to map out billions upon billions of galaxies, their positions, their orientations, etc., and use that information to deduce what the structure of the dark matter web of the universe actually looks like. So the LSST surveys will produce everything from what's going on in our solar system to what's going on the largest of scales in the universe. And in doing so, it is bound to pick out lots of interesting objects that can be then followed up with large aperture telescopes, such as the European Extremely Large Telescope. You can get an idea of its scale by looking at the people down here, or the individual person, or the people that are standing on this gantry. And that gives you a scale for just how big a 40-meter diameter mirror will be. Of course, collecting this much light will mean that these large aperture telescopes will be able to see very faint objects. Is that the largest one we can conceive of? The European Extremely Large Telescope on the bottom right there? Well, it's certainly the largest one under construction, but it's not the largest one conceived, because a little while ago some people worked out a feasibility study and said, is it possible to make one the size of that red circle? Is it possible to build a telescope with a mirror 100 meters in diameter? What would we call such a telescope? Well, we've already used names like the Very Large Telescope and the Extremely Large Telescope. So it's thought, rather whimsically, maybe this one ought to be called the OWL. The Overwhelmingly Large Telescope. At the moment, there's no funding to build such a thing. But if we can build the Extremely Large Telescope with a diameter of 40 meters, then it shouldn't be too many years before we can think about the possibility of even larger telescopes with diameters of 100 meters, or who knows, maybe even more. So if we want to understand what's going on in the universe, we need survey telescopes like the LSST to scan the entire sky and tell us what's out there. And we need large aperture telescopes to focus on particular objects in more detail. And we need space telescopes like the Hubble and the Webb working in the visible and in the infrared, getting above the limiting effects of looking through the Earth's atmosphere. All of these telescopes working alongside each other will allow us to get the data that we need to answer our current questions about the universe and how it works. But more importantly, these telescopes will reveal the questions we haven't even thought about yet. Thank you for listening to Keeping an Eye on the Universe in half an hour.